Thank you. It's a pleasure to be here this afternoon. I'm Eric Mansfield. I'm a senior product manager at IQM, focused on integrating quantum computers with supercomputers. So IQM has grown a lot in the last year or so. We're now at over 300 employees, and we've raised recently $600 million in total investment, including our Series B, just announced at the beginning of the month, for $300 million. Our product portfolio, which many of you could be familiar with, has three main parts to it. There's IQM Spark, our educational quantum computer that's affordable and starts at 1 million euros. Radiance, our flagship line, and Resonance, our cloud-based offering, allows you to access our 2054 and star topology systems. But today, I would really like to focus on Radiance. Radiance is not only our most advanced superconducting platform, but it was designed intentionally for HPC integration. It has a small form factor. It's designed to be upgraded inside of the HPC site. And it has a software stack that adds additional control to HPC centers that have the system on their site. Now, you might ask, why am I talking so much about HPC? But when we look at who our customers are at IQM, we'll see that many of them are the world's leading HPC centers, whether it's Jülich or LRZ in Germany, Oak Ridge in the United States, Ceneka in Italy, or IT4I in Slovakia. HPC centers are at the heart of our business. And at IQM, it's important that we do what we can to enable them, which is why this starts by really thinking about what's the mission of HPC centers. Their goal is to enable research innovation in the region that they're in, to advance technology, to deploy new architectures, new accelerators, such as when GPUs were introduced almost about 20 years ago, and also to strengthen the nation or region that they're located in. Now, this mission of giving new technologies comes with kind of a second goal, which is also core to what they're doing, which is sustainability. Whether you're the Lumi based in Kajaani in Finland, where you are using all the waste heat from your HPC center to heat the entire village, or you are Jupiter at JSC, the largest classical HPC in Europe, where energy efficiency is critical. You want to find a way to continue to grow supercomputing, provide cutting-edge resources, but be scalable. And this has become really a hard challenge. And these are just some numbers that we found some reports. Some pessimistic predictions say that in the near future, up to 3.9% of all greenhouse gas emissions could be tied to high-performance computing, and that the power demand could double in the next 5 years for high-performance computing, not to mention the outsized water usage for cooling. Which comes to our point, and this is the subject of this talk, really, which is combining quantum and supercomputing. So quantum computing, as we know, is uniquely good at high-complexity, low-data problems, such as the traveling salesman, chemistry applications. It has the unique superpowers of superposition and entanglement, whereas supercomputing is great at parallelized big data problems and general-purpose computing. And together, in the intersection of these two modalities of computing, we can find new capabilities for optimization, for chemistry, material science, and quantum machine learning. Now, if we look at this recent study from NERSC in the United States, they identified that over 50% of their ongoing workloads are ripe for disruption by quantum computing. And that's whether that's improving the time to solution, increasing the problem complexity that they can apply to, or improving the accuracy of the solutions generated. There's a clear path to quantum computing changing how supercomputing is done. Which is why I would like to introduce, just in a very cartoonish diagram, what we mean by a quantum supercomputer. So starting here on the right, we have our IQM Radiance, which is our on-premise computer. We are connecting it via a local area network, using an orchestration system such as Slurm to offload and send jobs to the classical supercomputer. And all wrapped around all this is that orchestration layer that makes it possible to run cutting-edge scientific workflows. So now that we have a rough idea what a quantum supercomputer is, I think the question becomes, why haven't we done this so far? And really, at IQM, we think that there's been three major challenges to making it possible to build a quantum supercomputer to date. First, not actually physically integrating HPC and QC resources. Finding a way to orchestrate quantum computers within the existing frameworks that exist at supercomputing centers, rather than trying to throw out the last 50 years of innovation in supercomputing. And lastly, providing easy-to-use building blocks to make it possible for all researchers to leverage HPC plus QC workflows. So I'd like to start talking a little bit about physical integration. So to date, if you notice, there's a large number of research papers that have combined simulators of quantum computers with supercomputers. And there also have been a number of theoretical studies, but we really haven't seen much in terms of physical integration until in 2022 at the Slush Festival in Helsinki, we demonstrated what we believe is the world's first HPC integration connecting our 5-qubit Helmi with the LUMI supercomputer. Now, don't get too excited. We weren't able to generate anything scientifically relevant here, but it was kind of a demonstration that this is possible. And then last year in 2024, we commissioned a newer system called QX based in LRZ in Germany. LRZ is the Leibniz Supercomputing Center. We've connected it to the SuperMUC NG, which is one of the largest supercomputers in Europe. Now, from working together in this period of time, we've been able to write up an honest report, an HPC guidebook of what it takes to integrate a quantum computer into a supercomputing center. And our conclusions, just to highlight conclusions, are that it is possible to integrate a superconducting system by carefully managing the location the computer is put within the supercomputing center, and that our system specifically was able to operate for over 150 days without any human touch except for a weekly 5-minute liquid nitrogen top-up. I would encourage everyone to read this paper. It's very interesting. So the second criteria we established is orchestrating via existing infrastructure. Supercomputing centers have been great at providing to their users access to systems. But quantum computers aren't usually accessed the same way resources are in a supercomputing center. So I'm sure many of you are familiar with this. I go online, I submit some circuits via an SSH terminal to an API. Perhaps you're using Resonance or AWS Bracket, and then your job goes into the queue, gets sent to an on-premise device, and then you get results back via the cloud. But this is not quite the experience in HPC. In HPC, we have this ballet of resource allocation, where a relatively small quantum computer cannot block a 500 million euro supercomputer, where there are many competing users who all need to have fair access to this rare quantum resource. And most important for HPC centers, we also need to be able to accurately bill and provide permissions to end users. Which is why I'm very happy to talk about some work that we've done inside the Munich Quantum Valley, an organization that IQM is part of, which is one of the first frameworks for bringing quantum computing into the supercomputing center. With this framework, we're able to standardize access for scheduling, job management, and device queries, so we can get back information such as current calibration state, QPU topology. We can be flexible across modalities even. And secondly, we have an HPC integrated scheduler and compiler that minimize idle time and optimize hybrid workflows. And lastly, I think this is one of the more difficult aspects, which is really providing the building blocks. So today, if you are a researcher doing hybrid computing, a lot of your work starts with equations on a whiteboard. You then publish a theory paper. Then eventually, you try to execute on a quantum computer combined with a supercomputer, but there's no sharing of code. And this makes it difficult for people to get started doing these types of high-impact research. So if we want to even back up further when we're talking about combining quantum computing with supercomputing, we see that workflows can be very coarsely put into two large areas. Either iterative workflows that go rapidly between quantum and classical, or sequential workflows where we start with classical resources. We go to quantum, and we end again in classical. So I just really like to hone in on this one, because this is what we see, the clear contribution of supercomputers today to quantum computing. So for example, I could use my HPC resources to prepare the quantum state, to perform a noise-aware compilation, or to use an algorithm library in order to get started. I can then run this on my quantum computer, and later I can post-process the results. I can apply quantum error mitigation, and possibly in the future, some kind of quantum error correction library as well. Now, doing all of this has led to some recent papers from using our machines. The first is a solid-state chemistry paper showing how the modeling can be improved by reducing the amount of resources required. The second is a paper that I'll dive into in a moment. And the third is a new way to simulate the transition of metals to insulators. Now, in this middle paper, we used researchers at the University College of London used a method called quantum selective configuration interaction, where they first started with quantum using a VQE to prepare an initial state, Hamiltonian, which was then sampled again on the quantum computer. And then these selective configurations were put onto the HPC for diagonalization and Hamiltonian generation. But what's really unique about this paper was how the researchers were able to combine different methods. So if you look here on this figure on the right, there is an active region and an environmental region. The active region represents 16 qubits that have been mapped individually to the electron cloud around these two water molecules. The blue region represents the environmental region, which represents the bulk solvent, as seen in this picture here on the left. So the researchers were able to combine a classical computation using the well-known LAMMPS package for the background solvent with a highly accurate and detailed calculation of the active region, which allowed them to then, in turn, compare how well these results stacked up against traditional methods such as Hartree-Fock above in blue, DRMG, density matrix renormalization group, and the QSCI described in this paper. And they showed that with QSCI, we're able to touch the regime of where we consider chemical accuracy, showing that there's a path forward for quantum computing to do things that are very difficult classically. And speaking of doing things that are very difficult, one of the things I introduced in this topic was creating building blocks. So that workflow I just described, we have found a way, and this is something that we will continue to develop, to reduce it to simple code that can be executed and well understood. So that workflow we just described is here in only 50 lines of code. Yeah. Now, going forward, we're very optimistic about the future. In this year, we'll be installing our new system at Oak Ridge National Lab and Chineka. This is an actual photo of the system. We've also received enough funding to continue growing and to be competitive. And in conclusion, we have built a quantum supercomputer. We have showed how quantum computers can be co-located with HPC, how we have the software framework we need, and we see kind of this promise of what will happen as we build the right building blocks to make it possible for more people to use HPC plus QC workflows. Thank you.